Hi, welcome to these tutorials on probabilistic functional modes. My name is Rezvan Farahibozorg, and this is part 1 of 3 lectures on this topic. Probabilistic functional modes, or PFMs, are a new FSL tool that are designed to characterize brain networks in population and individuals from fMRI data. In this first part of the lectures, I will describe the PFM framework and some of its key features. The second tutorial will focus on network matrix modeling in PFMs and compare the model to independent component analysis. The third and last part of the PFM lectures will focus on the latest version of PFMs, which is PFMs for big data, and show some of the applications of the model to date. The brain can be characterized with a set of functional modes. These functional modes are a set of brain regions that work in synchrony, in a way that they can be described with a single time course. Each of these functional modes are spatially laid out across the brain voxels. They can occupy one or multiple brain regions, and the way that they are spatially laid out across the brain voxels is referred to as a spatial configuration or topography. Once we extract the time courses of the modes, we can then find the correlations, temporal correlations, between the time courses and estimate the functional connectivity matrix. The functional modes can be estimated from resting state data, in which case we will refer to them as resting state networks or RSNs. They can also be estimated from task data. In this lecture, I will refer to functional modes also as functional networks, resting state networks, or functional components, and generally they all refer to the same concept, the functional entities of the brain. In recent years, there has been growing evidence that functional modes can systematically vary across individuals, in a way that they can be predictive of the personalized traits and pathology. You can think of it as somewhat of a diagnostic assay for the brain. In particular, there are two key aspects of the functional modes that vary across individuals. Here on the right, at the top, I'm showing two example modes for the population. In the middle, you can see how the spatial topographies of these modes are different between individual 1 and individual 2. They're different from each other, and they're also different from the group. Now, if we look at the time courses of the modes for individual 1 versus individual 2, if we find the temporal correlation between the modes for individual 1 versus individual 2, we can see that the values for temporal correlations are also different. So these two characteristics, the spatial topography and functional connectivity, are two key things that we want to be able to accurately estimate for each person and investigate how they are different across people. In previous lectures, you learned that the current standard technique to estimate subject-specific RSNs follows a two-step procedure. First, we apply group-level ICA to obtain the RSNs for the group. Then, we used a multiple regression paradigm, the dual regression, to map the group ICA networks onto every individual subject's fMRI and obtain subject-specific RSNs. In this way of modeling, because we drive the subject-specific networks based around the group, we do not include any explicit subject modeling. Additionally, because we always estimate the group-level ICA first and the subject-specific networks next, the flow of information is unidirectionally from the group to the individuals. In this way, because of these two key features, the amount of subject deviations from the group average that we can allow the model to accommodate can be limited. So if some individuals are very different from the group average, for example, patients, we may not be able to fully take that into account and to fully model that. Therefore, in recent years, there has been a lot of efforts to propose models that can simultaneously model the networks for the population and individuals. One example of these models is the Probabilistic Functional Modes, or PFMs, that was originally proposed by Harrison and colleagues in 2015. The core idea of the model is to allow for simultaneous modeling of population and individuals, where the group-level modeling of functional modes is used for top-down regularization of subject-specific modes, and subject-specific modes are used for bottom-up regularization of the group. By doing this iterative top-down and bottom-up regularization, the model allows for bidirectional flow of information between the population and individuals. Additionally, instead of deriving the subject space around the group, it includes explicit single subject modeling. And therefore, by including these two features, it aims to improve our ability to account for cross-subject variability. Now let's see how this model works. PFMs generally belong to a family of methods that are broadly referred to as matrix factorization methods. This type of matrix factorization are also used in many well-known methods such as ICA and PCA. Let's assume that we have an fMRI data of size voxel by time for a subject. We want to take this matrix D and decompose it into a set of spatial maps, matrix P, which is of size voxel by mode, and a time course matrix A, which is of size mode by time, and includes the time courses of the modes. So the spatial topographies of the modes across the brain voxels is captured by matrix P, which we also refer to it as a spatial map matrix, and the time courses by matrix A. We can also find the temporal correlations between the functional modes and estimate the functional connectivity matrix. Because the number of the modes that we estimate is typically much smaller than the number of voxels in the brain, this will reduce or this will give us a parsimonious summary of the high-dimensional fMRI data. Now let's see how exactly this is done in PFM framework. Let us assume that we have fMRI data from a subject S and a recording session R. We want to take this data matrix D and decompose it into a spatial map matrix P multiplied by time course matrix A, an additional variable H, which captures the amplitudes of mode activity over time. So how strongly the activity of a mode would fluctuate over time. We also have an epsilon that captures the residuals of our model. Therefore, our aim is to estimate this decomposition as accurately as possible for every individual in the population. However, this does not have an analytical solution. Therefore, we come up with a data-driven probabilistic approach to approximate a solution to equation 1. It is data-driven because none of the variables P, H, and A are predefined. We want to estimate all of them from the data. It is probabilistic because instead of estimating single values for the different variables, we want to estimate probability distributions for each of the model elements in the spatial versus temporal domains. And we want to estimate these probabilistic characteristic of the spatial and temporal elements, both for the subjects and for the group. For this purpose, we start by defining the type of distributions that we expect each of the model elements to have. For example, the spatial maps are said to be Gaussian. The idea is that for each voxel of each mode of each subject, we want to estimate a Gaussian distribution that can best explain our data. Once we define these distributions, the model's job is reduced to estimating the parameters that can describe these distributions. For example, a Gaussian distribution can be characterized by its mean and variance. So our model's job would be to optimize this mean and variance for all the Gaussian distributions that we have across voxels, modes, and subjects in order to explain our data. Now we have reduced our problem into an optimization problem. In order to solve this optimization problem, the PFM framework uses Bayesian inference. Let us assume that we have some true distributions underlying our data. For example, the blue distribution here shown here is the distribution for one of the model elements. However, we do not have access to this distribution. We don't know its type or its parameters. What we do is that we start with an initial estimate. This is the pink distribution shown here. As you can see, the pink distribution, which we refer to it as a prior distribution, is not a very good match to the true distribution. So the model's job is to optimize this pink distribution to obtain the red distribution that is as close as possible to the blue. This is a very challenging thing to do because we don't know the blue distribution. And we want to estimate from these priors a posterior distribution that is as close as possible to the blue. In order to solve this problem, PFMs use a technique called Variational Bayesian inference. I will not describe the details, the technical details of inference here, but you can read about it in Harrison 2015 paper. Now, some of you might be wondering that in this way of inference, our initial choice of the prior distribution can be important because if we have a good prior, our model will have a better shot at having a good estimation of the final posterior. So where do we get these priors from? In the PFM framework, the priors are sets like this. So we start with an initial estimate of the group level functional modes, similar to, for example, group ICA, but here we use group level variational ICA to obtain an initial set of group level modes. Then we will use this initial set of group modes to build priors for the subject-specific modes. At this point that we have the priors, we will optimize equation 1 for each of the subjects in the population and obtain the posteriors. We accumulate the evidence across individuals and feed that back to the group and obtain an updated version of the group. We iterate between these two levels of estimation until the model converges. Therefore, we have built a hierarchical model with two levels, group and individuals, where the two levels are linked via Bayesian priors. To define the priors and optimize the subject-specific networks, the model works around the following ideas. Firstly, it assumes that the overall architecture of the spatial topographies of the modes is consistent across individuals. For example, the overall architecture of the default mode networks, meaning the brain areas that it roughly covers, remain consistent across the subjects. Therefore, the group level spatial topographies can be used to build realistic priors for single subject modeling of spatial maps and optimization of the spatial map posteriors in equation 1. Now, if some of the subjects are very different from the group, the posterior distributions would deviate significantly from our prior estimations. Similarly, the model assumes that the overall architecture of the functional connectivity between the modes also is consistent across individuals, so that the group level temporal connectivity can be used to build realistic priors for subject-specific estimations. Unlike these two elements, we do not define a hierarchy over the time courses, because in particular for resting state data that is unconstrained, we can't assume that the time courses are aligned across individuals. We will talk a little bit more about how the priors are defined for the time courses in the next slide. This double hierarchy under spatial maps and temporal connectivity is an important characteristic of PFMs because it allows to accurately model subject variability in spatial versus temporal characteristics of the modes and disentangle variation in space versus time. In lecture part 2, we will talk about this characteristic in detail and how it can enable PFM modeling to yield more interpretable reflection of subject variations. Now that we learned about how the model works, let's have a look at some of its key features. The first key feature is what we already discussed, the simultaneous modeling of the group and single subjects, so that it gives us a unified iterative process where the group and the subjects are modeled together. This unified iterative process offers two key advantages. Firstly, the group model can be expected to learn richer population variations because it continuously gets updated based on the subject-specific modeling in each of the model iterations. Here, I'm showing an example default mode network, the group average and the group standard deviation of the default mode network. And as we can see, the areas where the default mode network has a stronger signal, it also tends to vary more strongly across subjects. Another key benefit of this simultaneous modeling is that because subjects are modeled explicitly, they can be quite different from the group, and we can accommodate that kind of deviation from the group. For example, here we show the default mode network in two example participants, and the area that is shown with that is marked with the arrow shows that some of the subnodes of the DMN can be misaligned between the subjects and the group. These somewhat subtle variations in spatial topographies can actually carry very useful information for characterizing individualistic traits and pathology. Another key aspect of the model is that it tries to estimate clean functional modes for every individual subject. In fMRI data, because we have non-invasive recordings of the brain function, the data that we obtain for a single subject can be noisy. So our estimation of the functional modes for individual subjects can also be noisy. When we do group level estimations, for example here I'm showing group level ICA, because the noise can be random, this can be cancelled out by averaging across many subjects. But if we look at these results from ICA Dual Regression, the single subject estimation of the modes can become quite noisy and become contaminated by the background noise. In order to solve this problem, PFMs proposed a solution. So before, I said that we use Gaussian distribution to model spatial maps in every voxel of every mode. It's actually two Gaussian distributions, not one. One of them is supposed to capture the actual functional mode, so the signal element, and the other one is supposed to capture the background noise. By doing this type of mixture modeling, we can separate signal from the background noise. Here I'm showing an example of a mode in the visual cortex, motor cortex, and the default mode network. And as we can see, the model is doing a good job of separating the signal from background noise for 3 example participants. Similarly, in temporal domain, the model builds mechanisms to separate signal from background noise. Here we're showing a time course, a noisy time course that is shown in grey, and a clean time course that is shown in blue. If we look at the power spectrum of the grey time course, which is shown in the middle here, we can see that there's a lot of high frequency stuff going on, which we know that the fMRI data, the clean fMRI data, should not have. When we separate signal from the background noise, these high frequency parts are gone, and as we had expected, we see mostly low frequency elements in the signal. The signal element in the time course modeling of the PFMs is constrained by a hemodynamic response function, which is what we expect from the fMRI data. Okay, now let's summarize what we learned in this part 1 of the PFM lectures. Firstly, the PFMs provide a unified framework that they can model the brain networks for the population and individuals simultaneously and hierarchically. In order to enable this, PFMs build a hierarchical Bayesian inference between the population and individuals in a way that they can be used for top-down and bottom-up regularization of each other. We define these hierarchies on 2 key elements of the model: the spatial maps or the spatial topographies of the modes, and the temporal net maps or the functional connectivity between the modes. By doing so, the framework offers some key advantages. Firstly, the group model, because it continuously receives updates from the subject-specific modeling, is expected to capture richer sources of subject variations. Secondly, because we do explicit single subject modeling, if some subjects are very different from the group, we should be able to accommodate that kind of deviations. And finally, because the estimation of the clean time courses for single subjects and cleaner spatial maps for single subjects can be very challenging, the PFMs implement mechanisms so that the signal and the background noise can be separated from each other. This is it for part 1 of the lectures on PFMs. Thank you very much for listening.